Hey guys, it's Jill here. Welcome back to Hardware 3D. In the last video, I introduced the probe design for dynamically querying drawable things, and we upgraded dynamic vertex with the bridge template pattern. Now we're going to put that tech to work and finally implement dynamic composition of our drawable techniques based on Assimp materials. We're going to reinstate Sponza with the new render queue technique system, and we're going to hook it all up to work with our dynamic probes. The first step is using the bridge with the dynamic vertex buffer to load vertex attributes from Assimp. So now what we're going to do is we'll write some code that can load mesh data from Assimp into our dynamic vertex stuff. So we add another constructor for vertex buffer here that takes a reference to AI mesh. And what we're going to do is we're going to loop through all the elements in our vertex layout. We get passed in a vertex layout. We use that, we move that into the vertex layout of our vertex buffer, and then we're going to loop through all those elements. We're going to bridge, so we need to pass in the runtime type of that element and two extra parameters. One is pointer to the vertex buffer that we're working with. Another is reference to the AI mesh. And bridge is going to template this on the static type of this thing. So if it's a position 3D, this is going to be templated to, type is going to be templated to position 3D. And all that's going to do is it's going to access the attribute at position 3D and extract the corresponding data from the AI mesh. And we're going to do that for all the vertices in that mesh. So we loop through the vertices. I is the index that's used to access the vertex in our buffer and also to access the vertex in the AI mesh. This extract thing is a little function that we've added to our map. So we can see here, each of our maps, they have a macro here, dynamic vertex element AI extractor. And it's templated on the name of the member that is going to be accessed on the Assimp side. So for position 2D and position 3D, it's just M vertices. But for the texture coordinates, it's M texture chords. For the normals, it's M normals. And that just expands to a static function called extract that takes the mesh, takes the index, and it returns mesh dot whatever member was parameterized in here at index I, and then we cast that to the system type, the type on the CPU side. Return that by value, and that's what gets stored into here. So we're using these template mechanisms to automate the code generation for all the different cases of accessing all the different members in an Assimp imported asset. Given a vertex layout, this code is going to read into the AI mesh and pull out all that vertex data and store it into our vertex buffer. And then I just write some code to test that out. But yeah, this allows us to now load our vertex data based on basically the instructions in this dynamic data structure here, which is one step closer to dynamically composing our entire technique, well, mesh/technique. But anyways, moving on. So here's where we actually write the dynamic composition stuff. So we're going to go back to material.h. We're going to complete it. We also added material.cpp. This is where all the magic is going to happen. But as you can see here, there were a whole bunch of other changes that sort of came in with that. So we look at material.h, the old code that we had in there that I just started, that was basically just me thinking out loud in code. So it's not very useful to look at the changes. You might as well just look at the file by itself. So we've got a constructor, constructs the material based on, it needs graphics, it needs AI material, and it needs path. This is the path to the model. Should have probably put that in the name here, but whatever. The model path. Then we got a bunch of basically helper functions. Extract indices. This is a helper. We'll talk about it later. Make vertex bindable and index bindable. These are helper functions. Make mesh tag. That just makes the, in our bindable codex, the tag that we're going to tag our meshes with, which is the combination of the path of the model and the name of the mesh. We'll talk about these helpers later on, but the real meat is in the constructor here in material.cpp. So here's where all the magic happens. Here's where the actual composition, the dynamic composition that I've been talking about for so long is going to take place. The actual dynamic composition itself, not so complicated. Basically what you do Well, I mean, you create a technique, our standard shading technique. We'll have one step, step 0, and shader code. I'll talk about this a little bit later, but this is actually going to dynamically select the shader that we use. So we'll start off with Phong because it's a Phong shader. And then what we're going to do is we're going to check the AI material. Yeah, we're going to check the AI material to see what it's got, what you got. So first we want to know, do you got a diffuse texture? And if you do, then we're going to add things to this material that, work with a diffuse texture. So if you have a diffuse texture, what needs to be added? Obviously, you're going to need to add a texture bindable. But for your vertex layout, we're going to now dynamically append a texture 2D. Because if you got a texture, you're going to need a texture coordinate. We're also going to append to the shader code diff for diffuse. And if the texture has alpha channels, we're also going to append mask. Now here's the thing, if you don't have a texture, then you're going to need some kind of a material color. And so we're going to dynamically append that to the pixel shader constant. So we're dynamically selecting what stuff goes in our vertex layout, what kind of bindables we get, and what stuff goes in our constant buffers, depending on what kind of things this material actually has. And then we do the same for other things about the material. Does it have a specular map? If so, we're going to add a texture for that. For the pixel shader constant, we're going to add a member to control whether we're going to use gloss alpha. And for the normal map, it's the same idea. And there is the dynamic composition in action. And then there's a bunch of stuff that is common for all shaders, right? Or for all these different configurations. They're all going to need a transform CBuff. They're all going to need blend states, input layout. Now, they're all going to need vertex shader and pixel shader, but different combinations are going to use different shaders, right? So how do you select that? Well, that comes in when we are concatenating with the shader code. So depending on what kind of stuff we choose here, we're going to get a different concatenated name. And to the end of that, let me see if I can find it here. Yeah, to the end of that, we're going to concatenate vs.cso and ps.cso, and that's going to give us our shader name. So we have to rename our shaders systematically to match this dynamic composition. And you can see here, I've done that for just a couple here for the test. Phong, diffuse, normal, pixel shader, Phong, diffuse, normal, vertex shader. And this allows us to dynamically select our shaders based on this concatenated name. And then down here, we can set different constant buffer parameters if they exist. So if there's a material color, let's set it based on the constant color that is in the Assimp material. Same for use gloss alpha. We'll set that based on, whether or not the texture actually has an alpha channel. And when all that stuff is all set up, then we add the pixel constant buffer. And then we're done. We're done the technique. So this isn't actually too complicated. The infrastructure that enables this, there's quite a bit of it. But once you've got that infrastructure in place, it's not that hard to compose together a technique. Compose it dynamically at runtime. Now, take this and, compare it. I've done this comparison before, but compare it to what we have to do to load all the different possible configurations in our mesh. So here we go, parse mesh, starting at line 265, and we've got our first, let me see if we can find our cases in here. So we got our first case, has diffuse, has normal, has specular, and then the next case, and the next case, and the next case, and the next case, and it ends at line 600. So that's what, 340 lines of code versus, maybe the 100 lines or so of code we got here. It's no contest. And another thing is when you do all those ifs together, you're basically working exponentially. Everything that you add to the mix that can be there or missing doubles the number of configurations that you might have to handle with if else. Whereas here you add one, you just have to add one more section in the code. So this is linear growth, and the other one was, exponential growth. It's a beautiful thing. Now, let's look at the other stuff that we got in here. Material.h, yeah, we'll go back to file view here. So after you have a material and you want to apply that material to a mesh, you're going to want to load the geometry data from that mesh based on the material. So the material dictates what members you're going to want to load. If the material has a diffuse texture, you're going to want to load texture 2D, right? So on and so forth. So the loading of the geometry is informed by the material. And so loading of the geometry happens via the material object. So when you want to load a mesh into an index buffer, you got to do it by calling it as a method on a particular material. It should be the material that matches that AI mesh. To be fair, I don't think indices doesn't have much to do with the actual layout of the vertex buffer or anything. So I just put indices in here because it's really the loading of the vertices that's the important part. So you see we have the function here, extract vertices. And what that's going to do is that's going to construct a vertex buffer based on the vertex layout stored in this material and the mesh. Because remember, vertex buffer has a constructor that takes an AI mesh and a vertex layout. And so because we have to load our vertices via the material, I figured might as well do the same for indices, keep it, consistent. And then you also have nice helper functions here that make a vertex buffer bindable from the mesh. And it just wraps around, it creates or resolves out a vertex buffer by extracting the vertices, and it also uses a tag so that you reuse the same geometry if it exists. And that's it. That is probably the most major part of this whole major upgrade to our system. And I hope you'll agree that's a pretty good upgrade. And then this one here, all we're going to do is we're also going to add a second technique for the outlining. And that's just what you've seen before. Nothing new here. So here's our first basic test of the material system. We're using Assimp to load a model, but we're only taking out specific mesh, putting it into our own drawable here. And, doing our thing here. We also got the outline effect that was added to the material. Then we got an update here that for controlling technique parameters. So what does this do? So in app.cpp, basically here, we're creating a new technique probe, inherits from, technique probe. And this one is going to be used with meshes. So yeah, in our simple test here right now, we're just loading the brick wall. So these tests are all done with the brick wall. And this probe is going to work on that brick wall mesh to be able to control a bunch of its parameters. Scale of the outline effect, material color, specular, all that good stuff. It's the same idea as when I introduced to you guys the probe system in the first place. So here you can see using our technique probe to control our effects. We've got our Fong effect, can turn that on or off, and we've got our outline effect. And we can control a whole bunch of things. We can control the color of the outline. We can enable or disable the normal map, change its weight, making it bumpier or flatter. Pretty cool stuff, right? Now, to start off with, for that simple test with the brick wall, I only needed a couple of shaders, but if we're going to load something like Sponza, there's a bunch of different configurations, so we're going to need a whole bunch of different shaders. So I have to rename now all those shaders to use the systematic naming that our dynamic composition requires. And that's what you're seeing here, basically. In material.h, here we go. So I moved a bunch of these functions into the CPP file. I also changed the naming so that it wasn't just VS, it was _VS. But yeah, that's it. Mainly just renaming the shaders to make them all systematic. All right, now we're coming in on the last major change that I've done here. And that is basically introducing the job technique system into our model node mesh system. So the first thing I did was I wanted to reorganize the model system. It's been a while coming, but originally and for quite a while, we had it all in a single .h.cpp system. Everything, node, model, mesh was all in that file. We just call it mesh.h and mesh.cpp, but that's not good organization. So I split those mofos up, and now we've got, model exception has its own thing, and also model window. That's the window that was used to show the controls for all the nodes in the node hierarchy. So those guys get their own, and then of course, node, model, mesh are all split up into their respective files. But there's nothing really amazing to go over here. I just split stuff up. That's pretty much all it is. What else did I change here? Stencil, just include some stuff. It's just a little bit of refactoring there's no real changes to be had here. There's a whole lot of work for some good organization, but not much to talk about. And then here, we are just now going to bring our model node mesh system into the 21st century by introducing the technique loading into that. We're taking model window out of condition. I left it in here just because I wanted it for reference without having to look back in the Git history, but it's going to be replaced by an external window that accesses the node data via a probe, right? So we can get this model window out of the model, which is, this should be an external thing to begin with. And I mentioned that in the video when I created it. And now we are going to make it external. So I'll comment that out. In the model loading code here, the constructor, we are going to parse all of the materials into our own material structure. And then we're going to load meshes based on our materials. And that's pretty much it. And parse node doesn't change here. Node.h, we comment out stuff that has to do with the model window. Some minor refactoring of these shaders here, these pixel shaders. Material color and specular color. They are 3-component as per our material system. So we had to change that and change some of the names to match up what we got in our material system. But yeah, it's not a huge amount of work here to get this to now work with the techniques and the material. Because, we've already ported over mesh. So it was really just model had to be ported over to use materials. And here we can see our first test of the material system used in conjunction with our model node hierarchy system. There's a little change here. What did I do? It looks like I just set the outline technique to default to being disabled. So I add the option to start a technique off as not active. Ability to scale model. So here, like when you load a model, I'm just giving you the ability to scale the geometry on loading. So when you're loading different models in the same scene, some models are really huge. You want them to match up with all the other things in the scene. So you have an optional way of scaling them here. So after I got all my testing done with the Goblin, we're going to now do it with Sponza. It's not a big deal, just uncomment some lines about Sponza. Well, we commented out the Gobbler. Set the camera to be, in a position that's better suited for Sponza. And Bob's your uncle. We're in Sponza. When you run this code, you see we're back in Sponza, except now everything's running on our new material system with the dynamic composition of the techniques. We're doing it. Now, here's the thing. We want now to have that window where we can navigate the scene nodes, click on them, and, edit properties of their meshes. So I create the model probe, and this is a different kind of probe. It gets passed around inside of the node graph. So we have the technique probe, which a technique will accept and then pass it down to the steps, and then it'll get passed down to the bindables. This gets, a model will accept a model probe, and it will pass it to nodes, which will pass it to other nodes, which will pass it to other nodes. So we see here, node.h, it has an accept that accepts a model probe, and that accept function will just, pass it to each of its children. And it also pushes the node onto a stack. So the model probe will have a stack, or it can have a stack. I mean, it's optional, right? There's a push node and a pop node. So when you inherit from model probe, you might want to maintain a stack that will give you some context, but you might not care. And then here in app.cpp, we actually make a probe, and it's quite big. It's a fairly large boy. So we had a technique probe, and it was named probe, and I renamed it to TP. And then we got a model probe named MP. And so what the model probe does is it goes through the entire hierarchy of nodes, renders the im GUI window to allow you to select the nodes with that tree list. But right now, all we got is the tree list from this, because it's only going through the nodes, creating that tree list. So here you can see we've got our node explorer back, but we're not actually displaying any information about the nodes yet. Next commit here, it seems like we're improving that scaling that we do on load. We'll see how that's done. And we're also doing full node transform edit. So instead of it taking a matrix, it just takes a scale now for parse node. So we look at mesh. Yeah, it takes in a scale now. And that scale is passed on to the drawable constructor. Drawable takes a scale, and now when you load that vertex bindable, it is going to take in a scale. So if we go into material, yeah, we see it takes in a scale here. And what it's going to do is while it's loading, well, after it's extracted the vertices, it's going to check to see if there's a scale that is not 1. And if so, it's going to loop through all those and just scale them. So the scaling now happens in the material when you're extracting vertices. I'm not going to lie to you guys. I don't remember why I needed to make that change, but it was a thing that needed to be done, and now it's done. It's not particularly interesting. What is interesting is now that we have that full node transform, let's see how that looks. So we go into app.cpp. We can see more code has been added. It's not a huge deal. It's just now we've got the first column there, which was for, you know, the tree of nodes. The second column now, we're going to have controls to control the transform that is applied to that node. So here we render the controls, and we have some functions to load the transform, resolve it out of our map of transforms, because we're storing our own cached versions of those transforms and applying them as necessary. So that's that. We're still not controlling the effects, but that will be coming. And I can see in our node tree here, we've got our transformation controls back. So we can rotate things if we like. We can translate them. It's all good. Now we reinstate our test boxes. So we got our test cubes. So we got our test cubes there. And what we're doing here is we're going to submit one before we do Sponza, submit one after Sponza, and show that the order doesn't matter. The problems that we had before, non-existent anymore. We can submit all these different things in any order we want, and when it gets all rendered, the effects will not get all messed up. Down here, yeah, just spawn those control windows for the cubes. No big deal there. We got our boxes back in the scene, and we can see that now they no longer care about, you know, their draw order with respect to the Sponza scene. Now, here's what I've been waiting for. Manipulating the Sponza techniques. So nodes can now accept a technique probe. And what a node will do when it gets a technique probe is it will pass that on to each of its meshes. So this is how we can inject technique probes into our system. But you might be saying, well, chilly, but the interface to the whole thing is model, not node. But model doesn't take a technique probe. Well, there's the interesting thing. What you do is you use a model probe, and that gets passed around to all of the nodes, and at every node, the model probe will inject a technique probe into that node, and the technique probe will go and do its dirty work on the techniques. So here you see I've added one thing to our technique probe here, but it's basically the same thing. And that thing that is added is controls for the specular map to turn it on or off. So here's all the things that this technique probe is able to control and generate controls for. And we removed the instance that was being created here. And now in model probe, if a node is selected, we are going to create a technique probe and inject that into the node. And then that technique probe will be passed all through the node to the techniques, to the steps, to the bindables, and anything that can be controlled will be controlled. That'll be rendered onto the window, and we can control it. And now you see here with the combination of our model probe plus our technique probe, we've got full control over all these parameters. So I can, turn on and off different techniques, and I can change their parameters. It's all good. All right, we're almost done here. 4 more commits. Set up Vertex shader constant buffer EX. So basically what this is doing is previously we only really had constant buffer EX for pixel shaders. Caching pixel constant buffer EX inherited from pixel constant buffer EX. So I've reworked things a little bit. There's a base class, which is just constant buffer EX. And then from that, there is pixel constant buffer EX and Vertex constant buffer EX. And the only difference is those ones have different binds, because one has to call PS set constant buffers and the other one calls VS set constant buffers. And then we have a caching constant buffer EX, which is templated. So instead of having now 4 things that inherit from Vertex constant buffer EX and pixel constant buffer EX, we could have pixel constant buffer EX caching and non-caching, and then Vertex caching and non-caching inherited. But instead of doing that, I decided to do composition. I create one caching constant buffer EX, which is a template, and you can template it on either Pixel or Vertex. And this one just adds the actual buffer cache, the dirty, the update, all that stuff. And then down here, where is it? You can just define caching Pixel constant buffer EX as this templated one using, and caching Vertex constant buffer EX as this one. So that's my way of basically avoiding code duplication by composing things statically using templates. Long story short, I just wanted a dynamic Vertex constant buffer. That's all I wanted. Why I wanted that, I'm not really sure, but well, here we've got an offset Vertex shader. So this is Vertex shader for an offset effect, and it needed a constant buffer, the offset, right? So, and I wanted that to be dynamic. So there you have it. That's what we did. Test cube. I mean, test cube here, they're both pixel constant buffers. But in material, no, I commented this out. Here is where I had the dynamic constant buffer, caching Vertex constant buffer, but it's commented out. It's a little bit of a weird one. I'm not going to lie to you guys, but you know, this was created almost 3 months ago. So I don't know what to tell you. I'm not sure. But I did one side effect that we can definitely be sure of is I did create a dynamic Vertex constant buffer thing. It was done. All right, moving on. Offset outline tech. Okay, so that was probably just I wasn't quite finished yet. Is what it was. So now we're finished. Here it is. There's the offset, caching Vertex constant buffer. There you go. Mystery solved. Add an offset here to the technique probe. And now you can have an offset outline effect. So here we can see the offset outline technique. And it works differently than the scaling one. It works by offsetting the vertices away from the model. So you can see you get a different kind of effect here. We'll talk more about the different outline techniques in the next video. Here we remove that model window stuff because it's not doing anything. It was just sitting around dead code. And the final change, very small. When you click on a node in the node tree, all I want you to do is activate the outline effect so that I can see it in the world. And I do that by, another probe. This probe, all it does, it looks for a technique named outline and it activates that technique. That's it. You can see here, you can just create these probes. If you need to do something small, you can create a probe inline and use it right there. No problem. For probes like this model probe, that's huge. I'd probably want to put it in its own file, and I will be doing that later on down the road. But you can also do these little inline boys. They're not too bad. The final change here, automatically outlining a node when you select it. Very nice for figuring out, which thing you've got selected. That's pretty cool, right? Just a useful little additional feature here. And there you have it. There is all those freaking changes. There was a lot of changes, a lot of stuff. I don't know how I'm going to edit this video down, to be honest with you guys. But I will do something, and there will be content. I mean, I said this many times during the video, but I hope and I think you guys will agree that these are some very nice improvements to our system. Taking things that were static, that were kludgy, copy and pasty, and making them dynamic and sexy and extensible. Things that scale. It's a beautiful time to be alive. Now, in the next video, what we're going to be doing is we're going to be playing a little bit more around with special effects. We've done the outline effect. Now we're going to do full screen effects. Effects that don't render any geometry, that just sort of apply a full screen filter, like a Photoshop filter or something, and that achieve some effect that way. Full screen filters, you can do lots of stuff with them. They're a very important part of a rendering graph. And I think you guys are going to enjoy this. Until then, thanks for watching. Hope you enjoyed this video. If you did, please click the like button, helps a lot. And I will see you soon with some more Hardware 3D.